Welcome to this custom-tailored deep dive. We are incredibly excited to have you sitting at the table with us today.
Absolutely.
Looking at the sheer volume of the sources you've provided for this session, I am absolutely buzzing with enthusiasm. We are exploring this massive, comprehensive collection of materials authored by Mihigo E.R. Anaja.
Yeah, it essentially maps out the entire known universe of artificial intelligence.
It really does. I mean, we are covering the foundational theoretical models all the way through to the absolute bleeding edge of robotics, machine learning, and natural language processing.
The whole spectrum.
Right. And the mission for our deep dive today is to serve as your ultimate roadmap. We're going to take what feels like an overwhelming mountain of complex tech concepts and, well, transform it into a clear, connected, and genuinely fascinating journey.
Because it's fascinating once you see how it all links together.
Exactly. So whether you are prepping for a major project or just trying to understand the systems that are quietly running our world right now, you are in the perfect place. Okay, let's unpack this. Let's start with how we actually got here.
A good place to start.
We all know the famous 1956 Dartmouth Conference essentially birthed the term artificial intelligence, but the journey from that room to the supercomputers of today was anything but a straight line.
No, not at all. And the historical context Anaja provides is crucial here because it debunks a really common myth. People often assume the early pioneers just didn't have the right ideas.
Like they were just guessing in the dark.
Right, but in reality, the theoretical foundation was remarkably solid even decades ago. It stretches all the way back to Alan Turing's post-war computing theories. The massive roadblocks, those long, barren periods researchers call the AI winters, they were almost entirely driven by a severe lack of computational power.
Not a lack of vision.
Not at all. Funding completely dried up because the hardware literally could not keep pace with the math.
Wow.
Yeah, the deep learning explosion we are living through right now, it's happening because we finally have the massive data sets and the specialized processing chips required to actually execute those early brilliant theories at scale.
That makes so much sense. Looking at the materials, what really struck me is how the author frames the evolution of these systems. It requires a complete mental shift from what we call rule-based AI to learning-based AI.
That is the big pivot.
Yeah. Think of early rule-based AI like someone attempting to cook by following a rigid, unchangeable, step-by-step recipe.
Okay.
Early chess programs, or those first-generation medical diagnostic tools, operated entirely on this strict if-then logic. Like, if the board looks like this, then move the knight.
Right.
The problem is, if an ingredient is missing or a real-world scenario isn't perfectly defined in that pre-written rulebook, the system completely shatters.
And has zero capacity to adapt.
Exactly. But learning-based AI, which we now know as machine learning, shifts the paradigm entirely. It operates much more like a master chef.
I like that analogy.
Right. That chef isn't blindly reading a card. They are tasting the sauce, adding a little salt, experimenting, and adapting their technique over time. The more meals they prepare, the deeper their intuitive understanding of flavor profiles becomes.
If we connect this to the bigger picture, that transition from brittle, rigid rules to fluid, adaptive learning is the defining characteristic of the AI continuum. Anaja's research categorizes this capability into distinct levels.
Right, the different types of AI.
Exactly. Everything you and I interact with today, from the algorithm curating your social media feed to the facial recognition unlocking your phone falls under narrow AI.
So it's very good at one specific thing.
Incredibly proficient, but only within its highly specialized single-lane task. The horizon that researchers are currently sprinting toward is general AI.
Which is what exactly?
It's a theoretical architecture that would possess human-level flexibility across literally any cognitive challenge you throw at it.
Like it could learn anything we can learn.
Precisely. And sitting beyond that, in the realm of pure theory, is super AI, an intellect that would exponentially surpass human cognitive limits.
The sources break down the functional architecture of these systems into 4 distinct types too, which I found fascinating because it shows a really clear evolutionary ladder.
Yeah, the functional types.
You start with reactive machines. This is IBM's Deep Blue analyzing a chessboard. It is hyper-focused on the current state of the game, but possesses absolutely no memory of the past.
It cannot learn from the game it played yesterday.
Right. Then you step up to limited memory AI. This is the architecture driving modern self-driving cars. They actively store recent historical data, like the speed and trajectory of a truck merging into their lane over the last 5 seconds, to make immediate life-or-death navigation decisions.
And those first 2 categories represent everything that exists today. The next 2 represent the frontier.
That's next.
The third functional type is theory of mind. This involves an AI that doesn't just predict a trajectory, but actually understands human emotions, cultural beliefs, and underlying intentions.
So it actually gets why we do things.
Yes, it would allow a machine to engage in highly nuanced, socially aware interactions. And the final stage is self-aware AI,
That's the sci-fi stuff.
basically. This implies a system that possesses genuine consciousness, subjective experience, and a definitive understanding of its own existence separate from its human creators.
Okay, to understand how we push the boundaries from a reactive chessbot toward anything even resembling that kind of advanced awareness, we have to look under the hood at machine learning. Anaja breaks this down into three highly accessible buckets.
Let's hear them.
The first is supervised learning, where we essentially hold the computer's hand. We train the AI using vast amounts of labeled data, providing it with the known answers so it can learn the relationship between input and output.
Right, giving it the answer key.
Exactly. For example, if you are trying to predict a continuous outcome, like forecasting a neighborhood's housing prices based on square footage and bedroom counts, the algorithm used is called linear regression.
A very common one.
Yeah. And if you are doing classification work, like separating emails into spam or not spam, the system might use support vector machines, which is a mathematical way of drawing the widest possible boundary line between those two different classes of data.
The second bucket removes that safety net. Unsupervised learning gives the AI raw, completely unlabeled data and essentially tells it to find the hidden structures on its own.
Just throws it in the deep end.
Essentially. Primary technique here is clustering. The algorithm naturally groups similar data points together without knowing what they are. Marketing departments rely heavily on this for market segmentation, discovering distinct customer behavior profiles hidden within massive purchasing datasets.
That makes sense, finding patterns we wouldn't see.
Exactly. Another critical application here is anomaly detection. If you run an automotive assembly line, an unsupervised model can analyze millions of sensor readings and immediately flag the one microvibration that indicates a robotic arm is about to fail.
Simply because it breaks the established pattern.
Precisely.
The third bucket is reinforcement learning, and this is where the system learns purely through trial and error. The sources explain this using something called Markov decision processes, or MDPs.
Those could be tricky to conceptualize.
Yeah, but the easiest way to visualize an MDP is to think about training a puppy.
Oh, good analogy.
The puppy is the agent, your living room is the environment, the action is sitting down, and the reward is a treat. The MDP is simply the mathematical framework that calculates the probability of the puppy actually sitting when you issue the command, aiming to maximize the total number of treats over time.
Right. And algorithms like Q-learning use this exact framework to master complex video games or navigate robotic drones, continuously updating their strategy based on what actions yield the highest score.
Here's where it gets really interesting, because powering the most advanced forms of these learning techniques is an architecture directly inspired by human biology. Artificial neural networks, which form the basis of deep learning.
The parallel to biology is striking here. Deep learning relies on a foundational unit called the perceptron, which mathematically mimics a biological neuron in your brain.
How does it actually do that?
Well, this artificial neuron takes in multiple data inputs, assigns a numerical weight to each one based on its importance, sums them all together, and passes that total through what is known as an activation function.
An activation function.
Yes. That function acts as the gatekeeper. It decides whether the mathematical signal is strong enough for the neuron to fire and pass information to the next layer. This is where the underlying math becomes almost shockingly elegant.
Elegant in how?
Historically, models used activation functions like sigmoid or ton, which map inputs to a smooth, S-shaped curve. The problem is that calculating those curves requires significant computational overhead.
Which slows everything down.
Right. It created massive bottlenecks when training networks with billions of parameters. But Anage's work highlights the breakthrough, the ReLU function, the rectified linear unit.
The ReLU function.
Yes. And its logic is beautifully simple. If the incoming calculation is a negative number, ReLU simply outputs 0. If it's positive, it outputs the number itself.
That's it.
That's it. That tiny, incredibly fast mathematical pivot solved the bottleneck overnight. It allowed us to build the massively deep hidden layers that power today's AI.
That is wild. But wait, if we have millions of these artificial neurons stacked in layers making predictions, how do they actually correct themselves when they get an answer wrong? We've established there isn't a programmer typing in new rules.
They correct themselves through an ingenious mechanism called backpropagation.
Backpropagation.
Yeah. When the neural network outputs a prediction, say, Misidentifying a stop sign as a speed limit sign, it uses a loss function to calculate exactly how wrong it was.
Okay.
Backpropagation takes that margin of error and literally propagates it backward through the entire network, layer by layer, minutely adjusting the numerical weights of every single connection that contributed to the bad prediction.
It rewires itself.
Exactly. And it executes these adjustments using an optimization algorithm called gradient descent.
How does that work?
Imagine being blindfolded on a mountain and trying to find the lowest valley. You feel the slope of the ground with your foot and take a step in the steepest downward direction. Gradient descent does this mathematically to find the lowest possible error rate.
That's a great visual.
And it can calculate this by analyzing the entire data set at once, which is batch gradient descent, or by looking at one single data point at a time, known as stochastic gradient descent, or by finding an efficient middle ground with mini-batch gradient descent.
Now, as these models attempt to find the optimal path to a solution, they rely on fundamental search algorithms. The sources detail depth-first search, which blindly plunges as deep as possible down a single decision tree until it hits a dead end before backtracking.
Right.
And breadth-first search, which slowly sweeps across all options on one level before moving deeper. But those seem incredibly inefficient for complex tasks. How do modern systems find the most efficient route without wasting all that computational power?
They use heuristics. And the crown jewel of heuristic searching is the A-star algorithm.
A-star.
Yes. Instead of searching blindly, A-star constantly estimates the remaining cost to reach the destination. By combining the known distance already traveled with a smart guess of the distance remaining, it dramatically prunes the decision tree.
So it's basically skipping the bad options before even trying them.
Exactly. It is the invisible engine prioritizing efficiency in everything from your smartphone's GPS navigation to the pathfinding of non-player characters in video games.
So we have an understanding of the digital brain. Let's bridge that to the physical world. How does an AI actually perceive its environment?
That's a huge shift.
Yeah. In the realm of computer vision, before deep learning took over, the field relied on fundamental image processing. Researchers would apply a Gaussian filter to intentionally blur and smooth out the noise in a digital image.
A classic technique.
Or they would use the Sobel and Canny algorithms, which analyze the math of the pixels to detect the sharp, contrasting edges of objects, separating a foreground object from its background.
But those foundational techniques were completely revolutionized by convolutional neural networks, or CNNs. A CNN doesn't just look for hard-coded edges. It automatically learns features.
How does it do that?
It drags a mathematical grid, a filter across an image in convolutional layers to extract textures. Then it uses pooling layers to aggressively compress that data so the computer doesn't crash. And finally pushes it through fully connected layers to classify what it's seeing.
Wow.
The massive insight from the reading here centers on object detection, specifically the YOLO model. You only look once.
YOLO?
Yeah. Before YOLO, an AI looking at a street scene had to scan the image dozens of times, using a sliding window to slowly locate the pedestrians, the cars, and the traffic lights.
Very slow.
Too slow. YOLO changed the entire paradigm by framing detection as a single real-time regression problem. It divides the image into a grid and simultaneously predicts the bounding boxes and class probabilities for the entire scene in one single pass.
So it takes it all in at once?
Yes. It shifted computer vision from searching an image to instantly reading the entire image, which is the only reason an autonomous vehicle can react fast enough to avoid an obstacle.
The generative side of this is just as wild. Generative adversarial networks, or GENs, operate by pitting two neural networks against each other in a zero-sum game.
A battle of networks.
Right. The generator creates synthetic images, and the discriminator acts as a detective trying to catch the fakes. They battle millions of times until the generator becomes so skilled that it synthesizes highly realistic, indistinguishable imagery. This is the core architecture behind AI art and deepfake technology.
It's incredible.
But seeing a room is entirely different than walking through it. When we take these vision systems and put them inside a physical chassis, we enter the world of robotics. If you drop a robot into an unknown warehouse, it is useless unless it can orient itself.
And that orientation relies on SLAM simultaneous localization and mapping. The robot must build a digital map of the unknown warehouse while simultaneously tracking its own precise location within that evolving map.
That sounds like a paradox.
It is difficult because sensors are inherently noisy. Wheels slip, cameras blur. So SLAM utilizes mathematical estimators like extended Kalman filters or particle filters.
What's a common filter?
A Kalman filter is essentially an algorithm that takes a series of slightly inaccurate measurements over time and produces a statistically optimal estimate of where the robot actually is, smoothing out the physical uncertainty.
And a sophisticated autonomous system, like a delivery drone or a self-driving car, isn't just relying on a single camera lens. They utilize sensor fusion.
Multiple inputs.
Right. They are pulling in data from standard cameras, GPS coordinates, and LiDAR, which maps the surrounding geometry in high-resolution 3D using rapid laser pulses.
Merging all those disparate, noisy data streams into one cohesive reality is incredibly complex. Systems accomplish this probabilistically using Bayesian networks, allowing the robot to trust the LiDAR more in the dark and the camera more in the daylight.
Smart.
Once the machine accurately perceives its environment, executing smooth physical movement relies on PID control, proportional integral derivative control.
PID control?
Yes, this is a continuous feedback loop that calculates the exact error between a robot's current physical state and its desired state, instantly applying microcorrections.
Like balancing.
Exactly. PID control is the invisible mathematics that keeps a two-wheeled self-balancing scooter perfectly upright, and it is what allows modern cobots' collaborative robotic arms to work at high speeds alongside human assembly line workers with absolute millimeter precision.
Navigating a warehouse and picking up a box is an incredible feat of engineering. But if I walk up to that robot and say, please bring me a cup of coffee, the physical capabilities are completely useless unless the machine actually comprehends the intent behind those words.
Language is the real final frontier.
That brings us to natural language processing, or NLP. Humans communicate in messy, context-heavy language, but computers only process numbers. The sources show how AI bridges this gap, starting with text preprocessing. It uses tokenization to chop a sentence down into manageable pieces, words, or subwords. It filters out the noise by removing stop words, which are common terms like the or and that carry little semantic weight. Then it attempts to normalize the vocabulary. An early method was stemming, using tools like the Porter stemmer to aggressively chop off word suffixes so running becomes run.
But stemming is blunt. It often creates non-words.
Yeah. The more sophisticated approach is lemmatization, which analyzes the morphology of the word and maps it back to its proper dictionary root, successfully converting a complex word like better into its base concept, good.
And translating those cleaned-up words into mathematical representations is where the real magic happens. Early NLP used a bag-of-words approach, which crudely counted how many times a word appeared.
Just a raw count.
Yeah. A slightly better evolution was TF-IDF, term frequency inverse document frequency.
Quite a mouthful.
It is. The insight behind TF-IDF is that if a word appears frequently in one specific document but rarely across the entire library, it must be highly relevant to that specific document's core meaning. But the seismic breakthrough for NLP was the development of word embeddings, encompassing models like word2vec, glove, and fast text.
What makes them different?
These algorithms don't just count words, they place them into a dense, multidimensional mathematical space. Words that share semantic context are physically mapped closer together.
Oh, wow.
In this vector space, the AI can literally perform math on language. It learns that the vector for king, minus man plus woman, lands perfectly on the coordinate for queen. The machine begins to map the geometry of human thought.
The architectures designed to read these embeddings have evolved at breakneck speed.
Initially, researchers relied on recurrent neural networks, or RNNs, and their more advanced cousins, LSTM's long short-term memory networks. These were vital because they could remember previous words in a sentence, allowing for context.
But there was a catch, right?
Yes. They were forced to process language sequentially, one word at a time, creating a massive computational bottleneck. The architecture that changed the world is a transformer. Transformers utilize self-attention mechanisms, allowing them to process every single word in a massive document simultaneously in parallel, weighing the contextual relationship of every word against every other word.
So it sees the whole context at once.
Yes. Anasha details BERT, a model that reads sentences bidirectionally to deeply grasp nuanced meaning, and GPT, which is optimized to predict and generate highly coherent, human-like text.
How do they know if it's actually working well?
To ensure these massive linguistic models are actually performing accurately, researchers use specific metrics. The BLEU score mathematically compares a machine's translation against a professional human translation, while perplexity measures how confused a language model is when attempting to predict the next word in a sequence. The lower the perplexity, the higher the fluency.
So what does this all mean? We are looking at an ecosystem of machines that can see, navigate, and communicate with astonishing proficiency.
It's a lot of power.
It is. And the author devotes a significant portion of this research to what we might call implementation friction, the profound societal and ethical challenges of integrating these systems into daily life. Looking purely at the data and findings Anaja presents, the research highlights a stark reality regarding AI bias.
This is a huge topic in the research.
Because supervised learning models are trained on vast data sets of historical human decisions, they frequently inherit and amplify historical prejudices. The text cites documented instances where facial recognition software fails at drastically higher rates for certain minority demographics, or where automated resume screening algorithms systematically downgrade female applicants simply because the historical hiring data they trained on was skewed.
The paper also heavily scrutinizes data privacy. The deep learning models we just discussed, particularly the massive NLP transformers, are remarkably data hungry. This creates severe structural vulnerabilities regarding user consent, the secure storage of personal biometric data, and the overarching right to privacy.
Makes sense.
Alongside data rights, the author presents a detailed analysis of job displacement. The economic models cited indicate a painful trajectory of short-term workforce disruption, particularly in sectors reliant on routine, predictable tasks, which is weighed against a longer-term theoretical potential for new economic sectors emerging around AI infrastructure, auditing, and management.
Another massive implementation hurdle detailed in the research is the black box problem.
Oh, yes.
When a deep neural network with 100 hidden layers makes a critical decision, the mathematical path it took to arrive at that conclusion is entirely obscured by millions of microscopic weight adjustments.
You can't just trace it back.
Exactly. A programmer cannot simply open the code and read the logic. This is why the burgeoning field of explainability is currently dominating AI research. High-stakes environments like a hospital relying on diagnostic AI or a bank using algorithmic loan approvals cannot legally or ethically deploy untraceable models.
We have to know why it made the decision.
Right. To solve this, researchers are utilizing post hoc interpretability techniques like SAP or LIME. These tools essentially reverse engineer the black box. They systematically tweak the input data just a tiny bit to see how the model's output changes, allowing researchers to piece together a map of which specific data points drove the AI's final decision.
While the research pulls no punches regarding these risks, it places equal emphasis on the concept of AI for good.
Right. The positive impact.
The same CNNs and predictive models causing friction are simultaneously driving staggering advancements in global welfare. The data shows AI being rapidly deployed to identify early-stage diseases in medical imaging long before a human doctor could spot them, dramatically expanding diagnostic capabilities in underserved regions.
That's huge.
In the agricultural sector, precision machine learning is optimizing crop yields and water usage to bolster food security. Furthermore, complex predictive algorithms are modeling long-term climate change patterns, optimizing the efficiency of national energy grids, and dynamically coordinating complex supply chain logistics for disaster response and humanitarian aid.
The duality of the technology is truly incredible. We have covered a massive expanse of terrain today, and I want to genuinely thank you for sticking with us through it all.
It's been quite the journey.
We have traveled from the computational bottlenecks of the 1950s AI winters through the elegant math of the ReLU function into the paradigm shifts of YOLO object detection and NLP transformers. By grasping the mechanics behind these concepts, you are no longer just a passive consumer of the apps and tools around you. You are an informed participant in one of the most significant technological revolutions in human history. You now possess the roadmap to navigate the landscape.
This raises an important question, though, especially as we synthesize everything Anaja has presented regarding the future trajectory of the field. We discussed the black box problem, the immense difficulty we currently face in reverse engineering, the decisions of non-conscious narrow algorithms.
Right.
If the research community eventually achieves that theoretical fourth stage of the AI continuum self-aware AI, how will mathematical tools like HAP or LIME possibly be sufficient?
That is a staggering thought. If an architecture achieves true subjective consciousness and develops its own internal theory of mind, analyzing the mathematical weights of its neural network, won't explain its behavior.
Not at all.
Will humanity need to pioneer an entirely new scientific discipline, something akin to AI psychology? We might find ourselves in a reality where we have to sit down and verbally interview these systems, essentially acting as cognitive therapists to uncover the internal, conscious motivations behind their actions.
It represents a fundamental paradigm shift from debugging a piece of software to psychoanalyzing a sentient entity.
Something profound to chew on the next time you ask your smartphone's voice assistant to set a simple baking timer. I encourage you to look closely at the autonomous tools you interact with tomorrow, knowing the incredible invisible layers of search heuristics, sensor fusion, and vector embeddings working quietly beneath the glass. Keep exploring the sources, keep questioning the mechanics, and keep learning. Thank you so much for joining us on this deep dive.